And today I'll be doing or showing you how to do project 2. Starting off, should probably pull up the assignment. Alrighty, so instructions are here. 100 length, Freestream of 2, density of 1.2 kilograms, and viscosity, we'll be changing that. So first off, we're going to be making this in ANSYS. So right now I'm going to look up Workbench. This is ANSYS. Pull that up. So as that pulls up, I can start It's nice to open. Okay. Solutionizing project, perfect. All right, so once this pulls up, you want to go to Fluent, double click, and then right click on geometry, and you click on design modeler, and that should pop up another window. Right. So once you're in here, I clicked on Z to make a 2D, and then I go sketch. I go to settings, make my easier to view. So it's going to be 1 meter. I'm going to choose it to be these parameters. I'm just going to put 1 and start my drawing. So start with the rectangle since we're doing a flat plate, and then press rectangle. So should do red right there, make it big. After that, I'm going to go into dimensions, just general, and dimensionalize this. I'll edit over here. So it's going to be 1 meter by 1 is what I choose, just to make my life easier. Since the length is 100 centimeters, divide that by 100 to make 1 meter. Once you finish doing the drawing, go to modeling, and you want to expand this to see the sketch. Go to concepts and go down to surface for sketches, and click on this, or you can click on the actual drawing and click apply for it to make the surface, and then generate. Perfect. Now that that is done, you want to go back to Workbench, make sure that it's updated. Since it is updated, you can now close this tab window. All right. I think I have 2 of them open, but that's not here or there. Now that I finished that, I'm going to open Mesh, double click. There's not many different kinds of meshes to have it open. But for geometry, do you want to go to Design Modeler? It's taking this time. Usually it's like a circle. There we go. This one, you just want to wait for the mesh the surface to appear before you start really editing anything. All right, perfect. Again, just press a Z to make it still loading. There we go. Now, so now it's, in 2D view for you. I'm gonna go to right click on mesh, insert, you want to do face meshing. So geometry, it should pre-select it whenever you do the inserting, and you apply. All right. After that, you go to back to mesh, and then generate. Should make some boxes here. Perfect. And you want to go back to right click on mesh, insert, and you want to do sizing. Alrighty, so sizing, you should be on edge and click on the top edge, apply. You want to change your element size to number of divisions. You can, my divisions are going to be in 50. Bias is no, but I don't want it to blend to neighbors because it'll like warp it. So I'll say no here. So I want it to be straight. So if when it was yes, it's a bit like different. You can't really see it because I haven't made the mesh, but let's keep no. So it's all equal. And that is it for that. Go back to mesh. You can right click on mesh and generate instead of having to go up to the toolbox task over here. See how straight. After that, right click again, insert, sizing, and now it's already automatically on that side edge. Apply. Now I'm going to change element size to number of divisions. We're clicking 70. And there is going to be a bias because since we're making a flat plate here, we want it to be more particular about what's happening down here than in what we're doing down up here. I choose the one that has like bigger and it gets smaller and smaller. There's different sizes. You want to make sure you want to click on this one. And then you define it as 60. And this one, since on this side, it's going big to small, so you don't have to reverse it. And you can blend to neighbors. Yes or no doesn't seem to be an effect on it. And you go back to mesh, generate. And you see it goes down. We'll do the same thing to the other side. Right click, insert sizing. It's just already on edge. Apply. One sec. So now that let's say, once you define the bias of 60, all right, you'll see that it's going bigger to smaller. You want to reverse that. So reverse bias, apply. Blend to neighbors, did I already reverse it? Oh, you got to click first on this edge and then apply. Yeah. To go back to mesh, generate. And that straightens it out. Alrighty. From there, you want to start defining. So you can go here if you're not already on select mode, edge, click, right click, and then go down to create name selections. This is your inlet. And then when you right click after you clicking on the edge, you just want to go down to create name selection. And then right click again. Okay. That's going to be our far field wall. And then this, most importantly, is going to be our plate. Cancel. I clicked on the wrong. Oh, maybe I didn't. I don't know. I don't know anymore. Perfect. When you close, everything's labeled. Good. You want to go back to Workbench. You see, it's still not updated, so you can right click on it, update. And then once it's green checked, now you can close it. If not, that means that not everything you've done has been saved. So you see, I can start setup. I'm gonna do double precision. I'm using student version, so I can't use multiple service processors because you need like a licensing for that. So let's just leave it as one for me as a student. That should be updating. All right, quick look if you want to see the graphics. See, it's inlet, outlet, and pump plate. A beauty. All right, so one thing I saw from this one video, you go to General, we already are. We want to check, and you'll see that more in the check and mesh, right? In the console. I don't know how to get it split here for some reason. I haven't been able to get it split. Maybe it's because I'm in the wide window. So it's done. Report quality. Assume it's done. All right. Now we go to models. So energy should be off for this. Viscous is going to be laminar. Okay. And that's perfect. Everything else be the same. Now we go to materials, fluid. So as you will see from here, it says that the density is 1.2, Freestream velocity is 2, and the viscosity of air is 1.8. So we're going to be mostly right now focusing on changing the air quality stuff. So if that will just please open. All right. Close. No, you're not doing solid, so that doesn't really matter. Motion definitions, we're not really doing anything here. Cell conditions, I mean, I show you, you don't really do anything here. Close. Boundary conditions, so very important. So I double clicked on boundary conditions to bring me to this task page. Inlet should be velocity. It should automatically see that. So plate with a wall. The only thing really changing is a far field. I want to treat it as symmetry. It's supposed to help with computation. Apply. Close. Okay. And that's done. Plate interior. So plate should be wall, outlet, pressure, inlet, velocity. Interior is just T interior. And then reference values. I found this to be very important for something else in data collection. For some reason, even though we updated air, it didn't update here. So we're going to be doing that too. I'll keep that same. And this is going to be 8. And everything else is the same. Oh, yeah. And then we will be saying that the speed velocity is 2. I don't think I forgot to define that with my boundary condition. For my inlet, we're going to define the velocity now. Should be the boundary. So when you look at the graphics, velocity is normal to this boundary. Yeah. And then 2. apply, close. All right, so I should officially be done with boundary conditions. Reference means you already did. So I guess that means we're done with setup. Now with methods, we double click. I'm going to do simple. Everything else should be kept the same. Now controls, kept the same. For definitions, on here, we want to right click, new, force report, drag. This is going to be helping us to our drag coefficient. So you want to, drag coefficient, because coefficient is not calculated as a, what's it called? As like, with respect to x, like as it, the velocity, how it changes, as it travels upon the plate, but rather it's done with each iteration that's done. So that's why you have to define it here first. You want to print to console. So when it does the continuity, x velocity, y velocity, and like the time and iterations, this should appear. A lot of people just put CD. I just, just to make sure I remember. And then click on plate and it'll be okay. And close. I'm not going to compute it because I'm not even to the point of initializing anything right now. Go to monitors, residuals. And when you double click on residuals, it should bring you to this page. 1 point, so is it 1E negative 07? The same for all of them. Oh, come on. All right. I mean, there's nothing here for us to really, okay, do there. So profiles, drag coefficient, perfect. Yes. That's good for monitors. I don't think we do anything outside of that. Yeah. So instead of hybrid, we'll do standard initialization. And we're going to be looking at from the inlet, because that's only really the fine thing. Oh, not sure why this is not 0. Should be 0. Did I forget to do something here? No. No. Yeah, I don't think I missed anything so far. Yeah, let's just go to initialization, 0, compute from inlet, and initialize. And then it goes by default, forget about it. All right. Now, after that, we want to go to double click on run calculations. You want to do a ridiculous big number. I found when I initially did this, it only takes like less than 200, but put a big number just in case. And we calculate. And it should appear in our console, really. Here we are. Beautiful. It is complete. Ooh, it didn't even crash this time. Look at that. Working well under pressure. So graphics, you'll see the scale, residuals, drag coefficient, mesh, whatever. So we go down to surfaces. Oh, sorry, close. I think graphics, yeah. Contours. The contours. We We want velocity. We do banded or smooth. I'm mostly seen banded. It doesn't really yeah, it's just a preference display. And yeah, you can see that happening. Now let's go to, you know, you could screenshot this, snippet, whichever. I guess you can't even screenshot it. I mean, in the Mac sense, because ANS doesn't work on MacBooks. All right, now same thing for vectors. Want to velocity, everything the same. I like it to be just arrow, not 3D arrow. It looks kind of weird. Save this way, and there, it's beauty. Okay, there. He's small, very small, close. So you take a screenshot of that too. The other video I watched talked about pathlines and particle tracks, but that wasn't really required for this project. So we can close graphics. Now let's go to plots. Don't recall doing anything with data sources, but let me check. No, it doesn't ring a bell. So for X, Y plots, one of the first things they want you to do, make sure you save these files. And you click on y-axis for velocity. And that stays the same. And you don't want to click, actually, you do want to click on plate. This is going to basically give you velocity profile. Oh, no. No. Yeah, sorry. You want to make a new surface because, I'll show you. It tells you in instructions that you want to know what the velocity profile is at these points. So not just what happens overall in the plate, but like at these different points, right? So let's make those points. So 0.25, and then that's 0.25. And y can stay the same for the first end, but last end to 1. So essentially what you just drew on here. Oh, I can't see the pan. Is like pretend this is 1.25, and you just draw a straight line up. And that's what we just did. Did I not save it as something? Oh no. And then you can save it as x equals 0.25. And create. Close. If you don't want to reduce the amount of files you have to download, you can just keep on going. I'm keep on going mostly because this is an example. 0.5, 0.5, 0.5, 1. Create. And then next one is 0.75. So like once you finish it and create it, it'll stay on. So you can technically just do the same and not have. Why aren't you typing? Equals. Okay. There. 25 and 1. Create. We can close because those are the 3 parameters that we wanted. So don't click plate X. Select them, and then you would, write it. And make sure you save it somewhere that you can view it, not just on Fluent. To download sometimes, whichever. Yeah. Oh, that's weird. So I just had, well, let's just say you just made new folder, project, XY. And, velocity profiles. And then all. So yeah, that's all of them. Perfect. Other than that, you close. I don't think there's anything else here. They didn't ask for velocity or pressure or anything like that. Close. And then from console, if you're wondering about the drag coefficient, you should be able to find it if you follow this. So it says Windows. All right. So what WBN is that? I don't think I know. What's app data? Huh. Yeah, you definitely make sure before you even start to have to find where you want this. So you got your velocity, you got your contour, you got the drag coefficient, you got your velocity coefficients. Let's see what else we need. Boundary layer thickness. So yeah, so that's what you did for the velocity profiles. Oh yes, wall shear. So for wall shear, you want to go again here, and this time you want to go wall fluxes, shear, x direction, and then with respect to the plate, right to file. So you'll have right project is already pre-selected, and then wall. And in the same wall fluxes, you should be able to do the skin friction that they ask for. So here, right down click, shear friction coefficient, and right, skin. Perfect. So both respect to plate. Let's see, what else does this project access to do? Tire coefficient, wall shear, yes, flat plate using Fluent, and that seems about it in terms of collection. Close. I mean, I guess you could. Well, the next to take screenshots for that. All right. I'm going to show you how I did my theoretical now. So no, sorry. One minute. So you're given kinematics, so we get the viscosity of whatever this is called, divided by the density. That gives you viscosity, kinematic viscosity. With that value, you plug it in down here with the given, Freestream velocity, which was 2, and the x values 0.235, 0.5, and that gives you these values. And then for skin friction, this is a formula, and this is a Reynolds number that we solved for here. We're just plugging that in down here, and that gives you our skin friction. For wall shear, here I did the actual formula that was posted on the what's it called, on the instructions for the project, right? But I ended up like rounding, and I'm not really sure how accurate that is. This one is more straightforward because it's gyro coefficient has to be over the length, entire length. So it should only have one value. So we will be comparing the percent error from what we calculated. All right, now I'm just gonna let's get down to sorry, yeah. So one key thing from that will help with like if you find yourself. Sorry, I'm just looking for the video file I have my documents in. So it's not quick access. Should be my OneDrive. No? You sure about that? Oh. Okay. For some reason it's not appearing, so just want to be a little bit more concise with how. File. Oh, sorry. Okay, let's hope I can get some information here. Yeah. So I can show you a quick way. That's not really. Nothing's quick. Since I didn't save it in somewhere that I can access. Lost it profiles again. Right. Okay. Velocity profile. Deselect them over the plate. I want to go down to wall fluxes, wall shear flux, right? And then skin friction. All right, let's check. Perfect. Everything's in there. I'm gonna go ahead and take a. Well, I'm not going to. All right. So now that we finished that, we showed you how I did the theoretical. Now we're gonna go back to here to look at our Excel. So velocity profile. Wanna basically get your number, your y values, right? So there's a formula that you can look up, and it's basically remember that you did 70 divisions and you did 60 bias, and there's a formula you can plug in, and it'll tourniquet all these y values to see the boundary layer. And to know where the boundary layer is, you put should be equal to 0.999 times the 2, which is velocity here. And you want to look for values that are close to this number. Since we won't have exact ones, you want to look for either the closest one, obviously. So here, I selected this one for 0.25 because it's wasn't a point. This one for 50, and this value for y. And that's going to give us our boundary layer thickness. So this is boundary layer thickness here. Shear friction. So once you Excel, you get the X value to be done for, and then you just put the wall and shear here and graph it, scatter plot. There you have it. Separate. So drag coefficient. Went ahead and I copied it from the console because I was having issues, like I did today, for downloading it. So there's a way for you to like copy it and move it around so you can just have it as a table here. And you just graph it iterations against the CD plate. Perfect. Now that you have all that information, you can then start make your comparisons. For comparisons, you have here theoretical results that we calculated. So this is given to us. So random number, I just plugged in because it's, I forget what it's called again. Yeah, it was a more direct number. For boundary layer, so I did the whole formula, 5 times x here, and divide by the square root of the Reynolds number. That's the Blausius solution that they want us to apply. Apply that on there. For CF, again, another solution that they gave us for a formula. And this to solve for skin friction. And then drag coefficient should be over the whole length, so we really only take this one to be a part of what you did. Because at the end of the day, these have iterations for when you do in Fluent, so you can't really compare it because they're not against the meters as it is here. So drag coefficient, same thing that I did for like this. I got it from these values. All right. Sorry. And CF, you get them directly from skin friction. So again, they don't do it exactly, so I can probably go down. So do 1, 75, probably did this one, 50, and then 0.25, probably would have done this one. So here, sorry. So that's obviously in backwards order from what's there, because I had for this you want to do the percent error, which is this value minus the theoretical. Oh, sorry, this value minus the theoretical divided all by the theoretical, and that gives you percent error. Does this every time. Yeah. All right. And from there, you can take that do your skin friction coefficient on versus your Fluent. They ask you for your boundary layer thickness, which we found here and here. Sorry, here. You just grab those two together. Obviously, in Fluent, you don't make it up to 1 because they didn't ask you for 1, but that's why it's a little shorter. And then, yeah, this one is wall shear comparison in Fluent versus vertical. So here are everything we did. We've got graphs of theoretical results. Friction. All right, that's it. Hope you enjoyed. And then that is both parts for the data set and the live set.